So I flew in very late last night, and then drove to my hotel, and I was doing the math, and it was like 1 o'clock when I got to my hotel, which for me was only 10 p.m. So I was reveling in, it's not that late, I'm fine, I can keep on going. But then I had to wake up this morning, and it was like 3 o'clock my time. So I hope I'm fully caffeinated and keep you going, but we might have to, someone might have to flip the lights to keep me awake. And I hope it doesn't rub off on you. I am excited to talk to you about this today because it's almost 20 years ago when I was an undergraduate student. I worked on a project in South Alabama. It was an old-growth longleaf pine stand. It was really this totally unique spot. It was sort of like you were describing. It was a 60-acre site that was on a major highway in lower Alabama. And we're reintroducing fire to it. And it was this group of people, and we're having this really great kumbaya moments. The Nature Conservancy was there. It was an industry partnership. It had folks from the state, folks from the Forest Service, and we're all huddled around with all this diversity of experiences. And in those fires, lots of old-growth trees were killed. Adjacent to the site, there was a trash fire one year, and the trash fire ignited and killed the state champion longleaf pine in the only state where longleaf pine is the state tree. So it was a nice wake-up call because it wasn't like we were a bunch of rookies out there. I was the only rookie in the group. It was a serious issue. So it's cool to come and talk to y'all about today. Here are my email addresses. Pick whatever one you want to contact me with. And do I have a little pointer or anything? Could you give it to me? All right, awesome, great. I always hate people do that, so I like to do it too. All right, what I'm going to say I and me today, what I mean is all these people. Kevin is in the room in the back, and he's going to talk about management stuff, but Kevin and I have been working on this issue almost that long. So it's important to give credit where credit is due. My PhD advisor, Jack Putz, and you probably know, University of Florida, Dory Gordon, who used to be with TNC, worked with this issue across Nature Conservancy preserves and other conservation lands. John Cushman and Ralph Melvall from Auburn University, both Dale Wade, now long retired from the Forest Service in Athens, and Joe O'Brien in Athens, worked on this quite a bit. Folks, when I was in California, we worked on this issue quite a bit. We had a field crew that was based in Gainesville, Florida for a few years. Bob Mitchell and the postdoc that worked with Bob Alibois. Bob worked on this issue for a really long time as well, and was, many of you know Bob and his legacy. I decided to work on it long after that undergraduate experience for my PhD. And I was arguing with my PhD advisor on a great topic to work on, and he said, well, you should work on this Duff stuff. And I was like, oh, great, whatever. I'm not working on that, and I took a road trip to talk to managers, all the best managers that I knew. And James Vernon was one of those. And so I went over to Eglin Air Force Base, and I was telling him about this really cool idea I had for a PhD dissertation that had nothing to do with Duff. It was bayheads and fire or something like that. And James gave me the very nice, oh, that's really interesting, which we all know what that means. And then he said, we have these issues with these Duff fires. And he kept on pointing out these spots. Like, I killed more old growth there yesterday. Duff. He was going through this. And I said, we figured out this problem, James. It's a really easy solution. You just go up to every individual tree and you put water on them. You can do it with backpack or you can do it with tractors. And he very calmly pulled over the engine and to the side of the road, and he said, I burn 1,000 acres a day. If I were to save 1 tree per acre, and you're with this putting water on them individually, you can start to do the math. And I realized at that point, oh my goodness, this is a real issue. And so seeing this many people is nice to see, right? It's a huge issue and it's much more complex than sort of simple solutions. A lot of the stuff I'm going to talk about took place at both at Eglin Air Force Base and the Ordway Preserve over east of Gainesville. I work with a group now that I work that I work in Seattle with on this issue because it is a national issue or international issue, and lots of other managers throughout the region, and lots of money from people that are interested in this topic too. All right, so you're here because you know that southern pine stands broadly and longleaf pine stands more particularly are imperiled. Right? This is not, we're not all managing the sort of Maserati or Lamborghini version of these ecosystems. Lots of them have extensive fire exclusion. There was a survey using FIA data done now some time ago that Ken Outlaw did, where he found in the states where they looked at the FIA plots, about half of the longleaf that was, half of the longleaf was not burned. So, and all the stuff we're talking about with longleaf pine and fire, you know, there was this very small slice where that was actually happening, but on the landscape it looked much more like this than those open pine savannas with pitcher plants and wiregrass. Really deep, heavy accumulations of forest floor, and a really, you know, diminished understory richness. There weren't replicated woodpeckers flying through here. This is the real scenario. Rather than the Lamborghini, it was more like the '68 Nova with the duct tape and the baling wire. And we know this is a serious situation, and it's super common. So structural changes, they're much more dense. Compositional changes, they have lots of other species that are there. The loss of the characteristic longleaf and upland pine fauna. And in this little note here, that there's an advent of the forest floor. Frequently burned longleaf pine stands, you don't, when you're walking up to a longleaf pine, you don't rise as you get to the bowl, right? And so this forest floor, particularly these Duff mounds or Duff donuts, as Kevin has called them, that's the dominant feature of these landscapes. So very different than open pine savanna. And so when fire was applied, and it still is applied to these sites, you all know what the results are, right? Heavy, large tree mortality. There were early reports were throughout the range from East Texas all the way into the Carolinas. Folks said, when we're putting fire back into these stands in the late 90s, lots of trees are dying, but it's not the small trees that are the most typically the most fire sensitive. It's the biggest trees, the biggest, and they would say the oldest as well. Then we know there's long duration heating, and that's been observed lots of times. Many of you probably have been bitten by this in the past. And persistent smoke, because what was happening in these Duff mounds was smoldering fire. In contrast to flaming fire, smoldering is slow. It tends to be really inefficient from a combustion efficiency standpoint. It generates lots of particulate matter. Because it's burning with such low intensity, it generates all sorts of weird compounds too. It's certainly not a CO2 emission pathway, it's a pathway with lots of weird noxious compounds. So none of those are good things. Right? So we did this a survey, Kevin, Jack Doria and I did this a decade ago, where we sort of documented this problem. These are a couple I think provocative shots. This is at Eglin Air Force Base, and maybe that's late 90s probably. And Eglin Air Force Base was a spot where this was happening like crazy. It was a natural resource organization that was working closely with lots of different conservation partners to restore fire to these landscapes. And this was the result pretty frequently. 400-year-old trees, patches to stands that were suffering mortality. And then this is the other common feature. This is just a gruesome looking photo of what we all assumed was this basal girdling. That's the state champion longleaf pine, or was, in Alabama. Okay. And what we found in this survey, or we reported in the survey beyond just this is the problem, was that it occurred over all landscapes, all ownerships, all levels of experience with this phenomenon. It wasn't like the rookies all did this or the Forest Service all did this. It was across the board. Okay, so I said earlier the real change and the sort of the insidious issue in these landscapes was this forest floor development and what we call Duff. So I'm going to talk a little bit about that. So you can't read that. Test your prescriptions. This is a nice slice of forest floor. So these little duff mounds sliced. We're all familiar with the surface litter, undecomposed, looks like litter still. And it decomposes to this pathway here to a fermentation horizon. That's what that really, really small font there is in the middle. Where you start to see breakdown. You'll see fungal hyphae in it. The leaves will still be recognizable. The other parts are recognizable. Lots of times you'll find both fungal hyphae and pine roots in that zone. Sometimes it's wetter than the underlying zone, which is pretty interesting. And then this underlying zone, the humus, not the hummus, is crumbly brown and unrecognizable. These two together, the fermentation and the humus together, we collectively turn duff. Okay. And you can see this beautiful white sand. The interesting thing also in this is, this is to remind me, there are roots in this. I said that there are roots in fermentation. There are certainly roots in humus, and we also know that there are roots in the mineral soil. And that has big implications later on. This is one of the reasons why a lot of folks will say, are you doing some stuff on duff in the Southeast? Yeah, there's a lot of duff work being done in the West. It does not work in the South for lots of reasons. One of those reasons is in the Mediterranean or extended dry season climates, this does not happen. It's not a good place to put roots if you're going to have no rain for 5 or 6 months. And so a lot of the work that we use, we borrow from them, does not work in our systems. Okay. How many roots? Well, I did this for part of my dissertation. Joe Bryan and others have done this as well. We've taken multiple cores through this. This is the most tedious and work you never want to do. You can see poison ivy or poison oak if you're looking at the plant above ground. It's more difficult when you're sorting through and the roots look like, that's not a pine root. So imagine yourself, anyway, there are lots of pine roots. In fact, there are either as many or more pine roots in surface duff, particularly near the bowls, than there is in the surface mineral soil. It's a terrible strategy for a longleaf pine to do this, and other southeastern pines to do this. But likely this is such a freak occurrence in its history that poor thing doesn't know any better. And so this becomes an important point later on. Lots of roots. That was what duff is. What is it? Well, in that undergraduate stuff that I did, and I piddled a little bit on this side project, my master's on it, and we used to call it litter. You got this deep litter around the base. And maybe it's because when I was a kid, I would rake pine straw in my yard and you put it up against your tree, right? It looks nice from a landscaping perspective. What is this stuff? I'm sort of giving it away right here. The mounds are dominated by bark slough. That's what those mounds are, right? If you go into them and you dig away, you remove this little surface needle cast, it's just bark slough. It makes sense because the bowl is there, and longleaf pine and the other southern pines, but in particular longleaf, it's easy to slough its bark, and so it's accumulating bark, and bark has a couple neat characteristics. One of them is that it doesn't decompose very quickly, right? So my incredible wine cellar, every one of them has bark in it, right? It's just cork. And so the stuff is extremely decay resistant. And the other characteristic in the ends of those bottles is that it doesn't let a lot of water through. And so it sheds water quickly. Those are both important characteristics. And so if it's really, really decay resistant, it's going to stay there a long time and accumulate. And so you tend to get these pretty deep mounds. That's 20 centimeters. That's pretty dang thick. Duff, we've measured it if you've measured it in flatwoods, you've ever dug around in flatwoods. The bars, this is up in some really non-productive sandhills, the bars look like that, right? It's what we used to call the trampoline duff, right? You walk into a site, the ground is shaking beneath you, right? Y'all experienced this. Okay, so basal duff, they're deep, dominated by bark slough, and across individual stands, and this is not always the case, but in sandhills in particular, it could be, one of the sites I showed you is about 40 years since fire. There's no litter accumulation or duff accumulation in those stands until you get close to trees, and then you have these extensive mounds, these aprons that are around individual trees. Whereas flatwoods or dense sites, you can be walking on duff the entire time, get to a tree, and have a slight increase, but not these tremendous increases. right? So they're discontinuous, and away from the stem, they tend to be dominated by, as you can see in this little thing here, 2 meters away from the tree, it's basically all litter. As you get close to the tree, it's almost all bark. Okay? All right, so that's all interesting. We talked about what the forest floor is. So I wanted to go through 2-ish topics. I'm not supposed to talk about any management stuff. Kevin is going to lead that, and that'll be totally awesome. I'm excited about it too. I'm going to talk about is the tree mortality part, because that's really why we're interested. Duff has a lot of other implications for understory plant diversity. Kevin's written some work on it. There's a lot more work that's likely due for this topic. The impediment that litter serves as for understory plants is tremendous. So there's all sorts of stuff we can do with that. There are all sorts of stuff with creatures that use those plants or use that surface habitat. But the overwhelming interest here is this link to large pine mortality. I'm going to focus on longleaf, but you can see the same thing in loblolly. You can certainly see the same thing in slash pine. We've observed it in shortleaf. Lots of species, lots of pines that have this general same phenomenon, but I'm going to focus on longleaf. Okay? I was a professor for 12 years, and I hate to just talk straight for an hour. So now is the time where I'm going to say, interrupt me, raise your hand, or just speak up, okay? So if I'm going too fast for something, or you have a question or follow-up, please do that. Okay. All right, so we get set up this is 2001, 2002 at Eglin Air Force Base. Kevin led this really cool replicated prescribed fire experiment. At the time, I thought, I was a graduate student, and I thought this is just what graduate students do. You have this, somebody goes out and burns 12 sites for you, and you have all this data that you collect, and it's really easy. We finished the last burn over that 2-year period, and we were sitting in a bar, and Roger Ottmar from the Seattle lab said, Roger's like 95 years old. Roger said, golly, I think this is the first graduate, because I was sitting there going, this is great, we finished. He said, I think this is the first graduate project I've ever worked on where all the burns happened. And anyway, so it's a pretty incredible project, incredible diligence by Kevin and others. Anyway, we set it up where we had these 4 treatments. There was a no burn, burn under wet conditions, burn under moist conditions, burn under dry conditions, and those moisture conditions are all tied to Duff moisture. They weren't tied to it's been pretty wet or KBDI or anything like that. They were all tied to moisture content. They were prescribed burn. Each site was 25 acres or larger, and we did normal fire effects on every site. So we were calling scorch, bowl char. We had Duff consumption pins at the base of trees. You can kind of get an idea. We can talk more about this in the woods. And then we surveyed mortality every 6 months. So something like 1,000 trees, the number of fuels plots, blah, blah, blah. It was a lot. Okay, it was sort of unprecedented at the time.
It was sandhill?
They were all sandhill, thank you. They're sort of flat woodsy, but not real flat woods. Flat woodsy if you've been to Eglin Air Force Base, but not real flat woods. All right, so I'm going to show you a few graphs. Overstory pine mortality, you can probably get an idea where this is going. And then here are our treatments. And we were funded by the Joint Fire Science Program to do this. It was very generous. I was a well-funded graduate student, had, Cadillac or something I was driving. We had to go and present and sort of show the funders what we were doing with their money, right? And it was weird because there were like 6 PIs, and then there was this graduate student, and everyone said, oh, the graduate student should go and give a talk. And I was like, oh, this is great, golly, this is great. And I had to present mortality results. And so we had done this, we'd spent $300,000 doing this project, and gone out and surveyed mortality. I was in Gainesville, that's in Eglin. You can start to get to how this would all go. This is 2001, 2002. Kevin's calling at 5 p.m. saying, it's going to happen tomorrow. You know, Ranger Camp, Zurich, whatever, you know, dry is going to happen tomorrow. I'm driving the 6 hours over, sleeping in the parking lot in my car. All this is happening, and then we're surveying mortality repeatedly. And so we went and presented, I went and presented, and here are my results from year 1. Here's the mortality. What's up with this? There's no mortality year 1. This is a really cool characteristic of duff burning. What's wrong with this graph? Why is there no mortality when we designed a study to kill trees? Well, if we look at year 2, we go to 18 months, we start to see it. So a real characteristic of duff burning is delayed mortality. This happens in the West as well, but it's really powerful in the Southeast. So 1,000 trees in this data set, 0 killed the first year. During the second year, really it occurred about 18 months following, you see, not surprisingly, tremendous mortality in the dry burn. And you can look at this in a couple different ways. One is the, we knew that, right? Do we need to spend that much money to figure out that dry duff burning kills trees? That's one way to look at it, right? I prefer the other side. And the other side of that was that in the moist treatment, it was not significant, the mortality was not significantly different than the unburning control or this burning under really wet conditions. So that's promise, right? This is the management application is looking that way, not looking over here and going, oh wow, dry duff apparently kills trees. We already sort of knew that. Okay? So that's kind of cool. Delayed, yep. And then that key point there.
What are you actually looking at with wet, moist, and dry? Those variables.
This is just that lower duff moisture content.
I know, but what are the break points of it?
This is 115% duff moisture, 85%, and 55%. So there's a handout I'm not supposed to talk about yet, but it's actually totally spot on. Yeah, does that answer your question?
Yeah, I was just trying to.
Okay.
Those were assigned to those they were not experimental treatments. You were not applying water to those to manipulate the moisture.
You got it. We're waiting for the fuels to get to the spot where we want them, which is why if you've done that, you know, basically we're trying to get a prescription that is a difficult one, right? Pushing it all the way to super dry, and then the others are pretty dang easy, right? This is sort of like day since rain process, right?
Yeah.
We didn't set it up that way because of the other complicating factors. All right. So this, we sort of knew, this is kind of duh, but this isn't. This is pretty cool. All right. The other part of it, remember, was not just mortality, it was large tree mortality. So if we look here, here's the wet burn. This is a diameter distribution here. Wet burn, the moist burn, and the dry burn. Well, what's the reports from all the managers across the region and our own experience in South Alabama was that the big trees died, right? That's the problem. I mean, if you killed 8-inch longleaf pine, this is not a story. This is the story, right? So in this case, it's actually, as diameter increased, so did the probability of mortality. And that's the much more tragic standpoint. These are eglin trees, so those are pretty dang good for eglin. Anyway, so the dead, in this case, the diameter of the dead trees is larger than the diameter of the live trees, which is totally opposite of what we should expect from all other tree mortality modeling. And trees larger than 16 inches in DBH suffered greater than 50% mortality, which is also what a lot of folks had observed and reported. Ouch, that's painful. This looks pretty dang good. Right? Again, so you can look at it right here, and I mean, seeing lots of mortality is one thing. Seeing the total reverse of what you predict based on all other fire behavior, all other fire effects models is interesting. But certainly this moist and wet is really neat.
So those are new dead trees, not accumulated.
You got it.
Each time you check, those are new trees that are dead.
Yeah. Yeah. Okay. All right. So we got the pattern now. And I'm going to start getting more and more into what's actually killing them if you care. We got some consumption and mortality. As duff consumption goes up, mortality goes up. Yeah, okay. If we look in particular at that lower duff moisture content, so as the moisture content increases, the duff consumption, okay, that makes sense, right? That all sort of is making sense. Duff moisture is tied to duff consumption, and duff consumption is tied to mortality. When we look at all the different drivers of mortality, if you close your eyes, ignore duff, what kills trees? If I want to predict longleaf pine mortality following fire, what kills them? Leave the duff out of this.
Residence time?
Okay, something's other. This is now, it's open wiregrass. It's the most gorgeous. It's the Maserati. What's going to kill those trees? Well, it's hard to kill them, right? So you're right. You're beating on your brain. All other species, scorch is overwhelmingly the dominant driver. If you have crown consumption, right, those needles are actually consumed. That's a really strong predictor of longleaf pine mortality. When we look at those individual that wet, dry, and moist burns, scorch was a predictor of mortality in dry burns. But duff consumption was a predictor across all of them. If you have large trees that have lots of scorch, what do the small trees have? Even more scorch, right? And so lots of folks will say, oh, well, you know, scorch, duff consumption, the overwhelming driver. Scorch is a relatively weak predictor. Okay? Let's dig into that a little bit more. Let's look at the mechanisms of large pine mortality. Y'all good still? All right, so the Ordway Swisher Biological Station now, just east of Gainesville. And we burned in a 37 years without fire longleaf pine stand. It's xeric sandhills, more productive than Eglin, not as productive as the Jones Center. I'll show you some pictures in a minute. Anyways, all the stuff I'm going to talk about, most of what I'm going to talk about is going to be sandhills. I'm going to give you a teaser with flatwoods, but this is going to be sandhills. Longleaf pine wiregrass, some upland oaks, deep forest floor, pretty characteristic situation. That's what it looks like there. It's kind of neat that 37 years without fire, you still see clumps of wiregrass, but just showing how low the productivity is. Again, we had some treatments that are replicated in this upland longleaf pine stand. Look how thin I was then too. God, that's great. I'm just going to stay here and look at that for a minute. Anyway, so we had these injury treatments. So it's a little bit weird. I think I have a slide. Yeah, I do. All right, so we had these injury treatments. We're trying to get at what's actually killing them. If I said right now, what's killing the trees, you're going to say girdling. Nope, good. Anybody going to go girdling? Because that's what I would have said when I started my dissertation. Because all the work from the West, from Douglas fir, ponderosa pine, people actually, it was posted on Facebook. This Duff Fire Science Workshop.
This one?
Yes.
Yeah.
And I put like, you know, because I'm totally on top of this. I'm gonna like stuff so fast. Don't test me. And then someone posted and said, yeah, back in the day we used. Apparently this stuff's been looked at for decades. And Douglas fir and ponderosa pine. And I was just like, you know, if there's an eye roll thing, I would have put the eye roll in there. I went into my dissertation knowing that it was girdling because all the Western stuff said girdling. Yep, and people will talk about it here, right? So I had that picture, that gruesome picture, it looked like it was girdling too, right? Anyway, so we set up these experiments to look at all this. We had to take care of, there's some root mortality. Jim Agee, retired professor at University of Washington, great fire ecologist, had found a place in the Southern Cascades where he said it was root mortality. And I just thought, those trees with all those roots, why in the world would we even look at that? But we'll look at it. So we had a root treatment that basically was, first we started with some flashing and fire shelter material, and I took flashing and wrapped around these individual longleafs, and then put the fire shelter material up 6 feet, stapled it to the tree. You can imagine how cool that looks, right? It was like this space age looking trees. It looked like big science going on. And what happened when I did that? The fire shelter material held up pretty well, But you have to be really careful when you're stapling and attaching stuff to the base, because what happened was it turned into basically a chimney in the base of the tree. And it was there when I was doing a check burn with the manager for the site, which really worked well. You have a lot of confidence in my abilities. Anyway, so we worked on lots of different methods, and the best method to not heat the stem but heat the roots was to physically remove the fuel away from the stem. We're talking like a 5 centimeter, 2-inch removal, just doing this. We used thermocouples to test it, we used thermal infrared images to test it, and indeed this worked. So anyway, here's the root treatment. The root plus stem is basically just burn it. That way the stem's getting heating, the roots are getting heated. The stem only was to put that flashing, take it away from the stem a little bit and make a little area that you're cooking this individual Longleaf. Steve Coates is an amazing dude, now with TNC, but was the research coordinator at Boardway for years. And then this control, we had 2 of them actually, we ignited it, and then as soon as it started to smolder, we put it out as fast as we could, so that we were eliminating the potential for long duration smoldering. For each of these, you can sort of see it here. Do I have a picture of that? I don't think I do. Here's a fire shelter material covered, loosely anyway, Pelican case that has data loggers where we have thermocouples, you can see. And this individual tree has thermocouples on the stem, surrounding it, up at DBH, in the Duff, in the mineral soil, all the way down to 8 inches deep. So it's at multiple levels. It's got something like, I don't remember, 16 or 32, I don't know what it was. There are a lot of thermocouples here, so this is heavily instrumented, and so we have a really good idea of how well these things work. Okay? So what did we find? Well, there's some heating that took place, and part of this validated our treatments a little bit. There's a lot of, I'm not supposed to put a table up ever, but there's actually something here I want to show you. The most important thing was that a quarter of all the burns had lethal temperatures. This is 60 degrees C, 140-ish Fahrenheit, at 8 inches deep in the mineral soil. You saw the picture of that site. That's not a heavy Duff site. It's been 37 years, but it's a super low product, it's a sand hill. 8 inches deep, it's got lethal temperatures. So when I presented this at that meeting where I had to show the year 1 results, and everyone was like, oh my gosh, you gave me so much money and you didn't find anything. This blew them away, because they were like, that's just impossible. Longleaf pine is not supposed to heat the underlying soil. There was early work in the 1930s that Hayward did, where he measured soil temperatures, and this is what we all know, right? How deep is the heating? It was a Forest Service scientist in the 1930s. He measured how deep the heating was in those frequently burned systems. There's no heat that's going down there, right? It's just a brief pulse, and it's not making it anywhere in depth, okay? But in these systems, somehow, you can look at them here, regardless of the treatment down here, here are those treatments I had. Seeing anything in these, seeing anything greater than 0 is crazy. Where are all the roots? They're in the Duff, and they're in the top 20 centimeters of mineral soil. All the fine roots are. And so, if the Duff is consumed, then you know you're losing that chunk of roots. If the top 8 inches of mineral soil is heated, then that's a really big deal, right? This is not using, we could have done this thing where we take some kind of integrated area that is total heating. This is just, we're going to say 60 degrees C because that's what people say. Okay, it's a very conservative estimate, and it's minutes beyond that. Each of these has minutes beyond that threshold. So that's a big deal. Lots of heat. And the interesting thing about these is, because I was a low-life graduate student, I couldn't get them to allow me to burn it overnight. And so I put these things out. At the end of the day, at 1800 every day, I put water on these individual trees, which is going to be an important thing later on. Okay? Is that camera still on? There may have been a couple nights where I didn't do a great job of putting them out, and I was camped there in my sleeping bag just to make sure. Okay, so that's the deep soil heating. I'm going to come back to it here in a second. I'm going to show you some pictures to wake you up. This is Eglin Air Force Base, a Duffy site. ignition has occurred, prescribed fire. This is a temperature scale. What's the ignition temperature for fire? Greater than 20 degrees C usually. So this is not flames roaring through here. This is below flaming temperature. So the fire has moved through the site. What do you see here? There's a longleaf pine. There's a longleaf pine. There's another longleaf pine back there. You can see this long duration smoldering taking place at the base of the trees. It's not crazy hot, but it's certainly hot, well beyond the threshold of, this is lethal if there's a root or a leaf there, right? So lots of substantial heating that's taking place. Okay, that's one image. Here's one of my faves. Here, this is a longleaf pine bowl. You see that? This is this Duff donut. Here's the temperature scale. This is 2 hours following flaming going away. So it's just smoldering. How long can that continue? Right? If you've experienced this, you know that can go on for an extended period, right? It can go on for days. So lots of heating. What else is interesting about this bottom right photo? It's kind of like a ooh-ah thing, right? That's kind of, oh, that's awesome. See how it's surrounding the tree? What do you notice about it 2 hours later? Yeah, the bowl is here. There's actually a ring around the bowl that's pretty cool. The bowl's not hot. You can see this right here. You can still see the bowl looks pretty dang warm. But the bowl here is not hot. And indeed, when we look at the thermocouples, where we have these thermocouples all over the tree, or we look at these images, that even the outer surface of longleaf pine is not that hot following these individual burns. So smoldering is taking place. It's taking place for days, but it's not. Why is it not doing that? It's actually pretty cool, right? This is pretty low temperature still. This is in and out of flaming potentially. But the heat transfer from this little tiny fuel here to that bowl is dissipated pretty easily. Right? This is like having a cigarette. I can put my hand close to that smoldering fuel. I can get really, really close to it. Its radiative power is not very great, but its conductive power in this case is pretty substantial. Okay. It was a late night. It was a very early morning. So the slide's not going to work that well. Just stay with me here. This is data right off the presses. I asked my postdoc this morning. It was 5:30 his time. He's on the bus in Seattle. Can you send me that image? All right. So you might be asking yourself at this point, why is he talking so much about sandhills? What about flatwoods? And all of our research so far has been on sandhills. Until this last year, we started to do some burning where we're looking at frequently burned, long unburned, in sandhills and flatwoods. So here is sandhill. This is at Ordway Swisher Biological Station. Frequently burned. The points are down here. There's no soil heating that takes place in those systems, at least no appreciable stuff, right? Nothing that really matters. The depth here, this is 8 inches here. So increasing in depth, and this is the duration above a lethal temperature. Nothing happening. Frequent. You guys surprised? No, we've known that for 80 years. Here's sandhills, long unburned. This is that same site, 37, it's like 50 years now since fire. They're still wired up. You see this, Tyler? So this is 8 inches deep. Here's the duration. Is this surprising to anyone? There's a lot of heating at the surface. It dissipates with depth. That makes sense, right? If we looked at the time course for these, I said that I had to put out all these fires back in the day, and more recently we don't have to do that. If you look at the time course, what you see I'll make a little graphy thing here. If this is time, and I'll draw some curves here for temperatures with depth. If you look at the surface temperature, it does this, like that surface mineral soil. It goes up high, and then it goes down low. As you increase in depth, right, you're going farther and farther down, it does this. It takes a longer time, right, because it's conductive heat transfer, right? It's the adjacent soil particle is heated by the adjacent soil particle, and this thing is progressing through the mineral soil. That 20 centimeter site, it does this, and then it does this. So it climbs, but it takes sometimes 24 hours for the stuff to climb. So that's not shown here, but you get, so that's important because I never looked at that early on. But over here we have some depths. That's pretty interesting. All right, now let's look at the flatwoods. That's what I wanted that thing to do. Number one, it's important to note these axes are not the same. So here we have 200 minutes. Notice what this one here is here. 1,000 minutes. You want to do the math on that one? It's just a long time, right? The flatwoods frequently burned. There's not much going on again. Just like with the, it's not surprising again, right? This is biennially burned flatwoods in Alachua County. No soil heating taking place. How about in the Longleaf burn? 40 years without fire, productive site. That's a lot of heating. Interestingly, the pattern in heating is different. Not only is the magnitude different, but the pattern is different, right? This is lots of surface heating, it diminishes with depth. This is lots of surface heating and lots of heating at depth. Not surprisingly, that site, there are not a lot of live, living trees right now on this site, but let's not mention that to anyone. Okay? All right, so there's a lot more to be learned about this with flatwoods. Okay, does that fit some people's experience? Yes, has lots of head nods. Okay. Okay. All right, so I'm going a few more pieces of evidence. Are we okay on time? All right. We found mortality, which is interesting, right? That's what everybody wants to see, but there's also a lot of stress in these individual trees, and we want to be able to tie that stress to why the trees are dying. I always think about it that if the more we know about the underlying mechanisms, the greater the potential that we go, oh, I found a way to trick this. Here's a way we can intervene from a management standpoint and eliminate this individual stress. Maybe we burn it at a different time, perhaps we do this when we're watching weather, maybe we're, all these sorts of tricks that we can do that. Perhaps we thin and alleviate local stress, other ways we can get at this. And so bear with me on a couple of these. They're a little bit dense. All right, so here's percent forest floor consumption. This is litter and Duff together, and this is pre-fire sap flow. What's going on in this one here? As consumption increased, what happened to sap flow? It diminished, right? Pretty steep in this initial phase. This is a piecewise fit here, but pretty steep decline in the initial phase. So as any sort of consumption is taking place, and then beyond some threshold consumption, which is what you find a lot in trees that are going to die, a threshold, right? You're in a living, you step over the threshold into death. You find this pattern a lot, lots of threshold stuff. If we look at carbohydrates in the roots, basically their storage, we find that their duration of heating here, this is a log scale, but the minutes of lethal heating, as that duration increases, what happens to their coarse root carbohydrates? They decline at a pretty rapid rate, which is interesting. If you look at fine root carbohydrates, you don't find any change. But coarse roots, you find substantial change. Our hypothesis was that the fine roots, we dug up fine roots, and then we dug up fine roots. You dig up coarse roots, this is pre and post burn. You dig up coarse roots, you dig up coarse roots. The fine roots were just turning over in this process. They're being replenished by the stored carbohydrates in these coarse roots, and the poor coarse roots are there just basically, let's drain this, where they're draining the coarse root carbohydrates to replenish those fine roots. Okay. Both of these point to a root issue, not a basal injury issue. So no evidence from the surface heating, all our intensive measures on the bowl, it's not gurgling, and all of our measures tend to be focused, or tend to show this, this root heating signal. Okay, so short term, there's some stress. Well, we decided a year and a half ago to go back to these sites where I had subjected these trees. Very few trees died in that experiment. It may have been that I put water on them that afternoon at 6 p.m. Could be that the end of that experiment was the wettest year in 50 years. You know how that kind of stuff goes. But they were stressed for sure. They saw steep carbohydrate losses. We also saw radial growth differences. The longer they were heated, the less radial growth they had, right? That makes sense. So then we went back and looked at resin ducts and also radial increment, 10 years later. And what we found was that if you look at all that root plus stem, and control, they basically didn't differ in growth over a 10-year period. Averaged over a 10-year period, no change. But during drought years, and over that period, right, they were burned in fall of 2003. Over that 10-year period, there's some pretty amazing droughts in north central Florida. And every one of those drought years, what happened? Growth was almost through the floor on the trees that suffered the greatest heating. The greatest below ground heating, those trees had depressed growth. During normal years, they were doing just fine. They were actually a little bit exceeding some of the growth, but it's super minor. But during the drought years, there were 3 drought years, the 3 driest years, each of them had much lower growth. So they took that on the chin initially, and they're weakened even a decade later, which I think is troubling in a lot of ways, right? If we look at mortality, I said we did it every 6 months. After 2 years, we never went back to those sites, right? Whatever, they've gotten all the mortality they're going to get. Let's move on. And if you're in the Southeast, they're going to burn that site again, right? In the West, where they have infrequent fires, they've looked at post-fire mortality and then tied it to initial injury, and they find that it can take 9, 10, 11, 12, 13 years to capture all that pulse of mortality if they relate it to individual injuries. And so it might be that we've been looking at this problem in a really simplistic way that ignores what's really happening out there. Okay? Bummer. Sorry about that. Okay. I'm not going to step into Kevin's, but I do want to talk a little bit about, this is a more complex issue than just like a cartoon drawing of a mantle of forest floor consuming and trees perishing, right? There's some physiological stuff that I kind of wave my hands a little bit about, but why is it that it looks like this? There's a bowl of longleaf pine, here's a little white ash patch here, there's another one right here. If you've burned in these sites, Greg, you were saying this morning that sometimes a couple trees will ignite and the others will not ignite. The overwhelming observation from the field is that consumption is patchy, right? Some of the stuff we've done, we've looked at individual cones as vectors for ignition. An individual pine cone, this individual pine cone here, while seemingly small, you see the little devil? You got to look really closely to see that, right? Do you see those little devil ears? An individual pine cone will flame for a few minutes, but the dang thing will smolder for 45 minutes. The same longleaf pine litter in the same area, the same volume of longleaf pine litter, will smolder for about 4 or 5 minutes. So extremely long. And what we found in a lot of these, if you do this kind of work, it's much like watching paint peel, metal rust, standing around watching Duff smolder for a long time. What we found was that woody fuels tend to make little areas of consumption, right? You've seen this sort of thing in the woods, right? Where there was a log burning, you can see after. But smaller fuels, in particular pine cones, they burn much longer than small woody fuels do. And you'll see this pock-marked surface. And interesting thing about pine cones and the stuff we did with those individual tree burns, we collected all these different parts to look at their moisture content. And when we collected the cones were drier than the surface litter. In almost all cases, cones were drier than surface litter. Their structure is interesting. They open up when they're dry. What happens when a pine cone is wet? It's awesome to throw at someone, but when it's dry, it's very difficult to throw, right? So they open and they're a porous fuel that can get really, really dry. So a dry cone, what else do they do? I always said they ratchet down. You see cones that have needles in them, that's because they're opening and closing, and they can also descend a little bit into the forest floor. They ratchet down when they wet and dry. And so they can ignite underlying fuels. There's also a lot of variation in space with moisture content. If moisture content is the primary driver, and there's a threshold, like I said earlier, for consumption, sometimes there's some really dry spots. What's the driest spot of it? Here I am, this wall over here is the bowl of longleaf pine, and drip line is the edge of this light. And I were to sample moisture content days, let's say a week and a half since rain. Where is the driest spot? I got out in the sun out here, that's awesome. Here I'm at the drip line, and here I am at the bowl. What's the driest spot? Well, it depends on a few other factors, right? So you don't want to answer just yet. What's your guess?
Outside the drip line.
What's that?
A few inches out.
From the bowl? Okay. Someone else is going to say something?
Outside the drip line.
Outside the drip line is what we always thought, and what you find consistently is it's driest over here. It might be that there is substantial interception from the crown during rainfall events, right? It might be that, because there's not a lot of stem flow taking place, right, in rough longleaf pine bark. So there's the interception loss, but there's also the characteristics of the duff that's there, right? The bark slough is not going to retain moisture very well. It's going to shed moisture rapidly and move it into the mineral soil. There's a lot of stuff to look at with that. We've done some stuff looking at how it varies in space, but also how it varies in time, looking at time since rain. Yeah, right.
So that leads to where do you take your, because we do a lot of duff moisture sampling. And where you take that sample makes a big difference.
Yeah.
So in your study, when you were getting ready to do the ignition, where did you take the sample? Because you can make it almost say what you want by where you take the sample and how deep you actually do the moisture content analysis.
Yeah, so
And
that's a great point. So we were talking about that either, it was this morning, I know, but it might have been last night this morning, not this morning. In our Eglin study, we had a number of samples per site. There's strong, we've found subsequently from Eglin and from Ordway, and what you already know, there's a lot of variation in space, right? So individual burn units having a duff moisture value, that's ridiculous, right? You could have variation that is not an order of magnitude, well, I guess you got order of magnitude, but certainly you can have a doubling, right? It's 100% here and 50% there. If it's a threshold, and the threshold we think is somewhere around 60%, it's actually, I'm not totally sure about it, but 60% is what folks will use, then some of the sites are below the threshold and some are above the threshold. That's terrible. That's the worst case scenario, right? In our individual tree burns, we were taking moisture content samples from the spot we're burning, so that's actually a lot better. But that other one where I'm showing duff moisture content, what Tim and I were discussing this morning was, it's amazing that the relationship's so good, right? Because there's tremendous variation. And I think that complicates everything. This temporal part of it is also a little bit of a complicating. Immediately following rain, there's not much variation in moisture content, right? It's all wet or very wet. But as you have that protracted period without rain, then you start to see these differences. The spots that are sunny out beyond the drip line, they're drying. The spots that are at the bowl, perhaps they're drying, maybe they didn't get that wet initially. All right, so you start to see this stuff break apart, and that's where it matters, right? It doesn't matter if there's spatial variation following a heavy rainfall event, right? It's really, really wet way beyond the threshold, or really wet way beyond the threshold. It's when it gets to that spot near the threshold that's important. And this is a problem. That's a problem, Greg. Trying to figure out where to do that. Oh yeah, they vary in space. Okay, so I'm going to wrap up. Okay, still time?
Oh, you're good.
All right. That's a major threat. Working on the 68 Nova with the baling wire and the duct tape is something that we have to do, right? It's unavoidable. The forest floor in these systems is a serious threat to conservation. Duff fire causes mortality, also a serious issue. I talked a little bit about pine stress and mortality. Maybe I could keep on talking about it. Kevin's certainly going to talk about it as well. And we know that duff consumption is key, and duff consumption is messy because it's driven by moisture content. There's some other drivers that are important, but moisture content is the one we can manage. If you look at the literature on duff consumption, I'm not supposed to add new stuff at the conclusion, but I'm going to do it. Bulk density matters. right? How porous that fuel bed matters. But our ability to manipulate that is really small. The only thing that we can manipulate in these stands very easily is moisture content, right? We capitalize on days since rain. We understand a pattern and we can capitalize on that. And we know that moisture content is driving a lot of consumption. And so getting a better handle on that relationship, not only at a stand level, but at a smaller scale is really key. And much to learn. I wasn't that skinny there, but it is still better to look at the pictures. All right, that's all I have.
So could you circle back to what
Yeah.
the current thinking is of those drivers of the mortality? Just to put that back in your
Yeah.
because I think that's
What causes tree death? Well, it's not known what causes tree death. What we think causes tree death is that it's that fine roots are consumed during fire. We have a lot of evidence. That flatwood shot I had, this thing here, is even more damning. But we know that in the surface mineral soil, not the organic soil, there's a tremendous fine root proliferation. We know that they're in the Duff. If you have 100% Duff consumption, you likely have something like 40 or 50% root consumption. You've lost 40 or 50% of the fine roots of the pine, which is just like mind-blowing, right? What if we're off by half, and maybe it's only 20%, right? There's some redundancy in these things, but you lose, if it's consumed, those roots are not sitting there in the air going, that was a tough fire, we made it through, right? They're not doing that. So beyond that, though, if we have, in the heating that we showed from Ordway, if we have heating that goes down 8 inches deep, now we're at 90-something% of the tree's fine roots. And so, we've killed the fine roots, particularly near the bowl, something that Bob Mitchell and I discovered at Eglin. It was pretty hilarious. If you know Bob, and you were ever in the field with him, this will be really funny. They were in the field together, code word crazy, and we're excavating pine roots. And we're at Eglin and in these sand hills, and Bob's sitting there very uncomfortable, and we're digging through, and we're pulling these fine roots, we're putting them on, and then liquid nitrogen, all this, this is hardcore sciencey thing. And at some point, we look over, and the root that we're excavating, this little fine root, it goes back into this main stem, right? They're much like river networks. This is a lot of Bob's work was looking at the branch order, much like you look at the stream order. So we're looking at the little fine headwater streams, right? And we're sampling these roots and being very careful to keep them at a certain temperature and bag them. And we look back at the main root, and the main root is killed. It's saturated in resin. You can see where it had burned. That entire main root was killed. And so anything that's happening out in these fine roots is immaterial, right? We're going, I hope that our handling of it takes care of it. So we know there's substantial fine root mortality. What we found when we looked at root carbohydrates was that the coarse roots, falling fire had this really deep decline, and the decline was based on heating. And so what we hypothesized was that as they kill the fine roots, a tree is going to replenish those fine roots rapidly, right? Post-fire is a water stressful period, and so to rebuild those fine roots, what are they going to do? Take the stored carbohydrates from the coarse roots and replenish. And that seems to make a lot of sense. We're going to stick with that right now. We're not totally tied to it. They're suffering some other stresses too, but we find that growth is related to that deep heating. We find that growth was not related to bark heating. None of our measures have ever been related to bark heating because, like that image showed, that 110-minute thermal IR, it's cool to look at, sort of like looking at that mortality. The dry burns cause a lot of mortality. That's not the part of the graph you have to look at. It's moist burns actually can reduce Duff and not kill trees. That's the cool part of that graph. For the thermal IR, oh, it's so hot around that tree. It's actually not hot around that tree. It's hot in the Duff surrounding that tree, but the bowl was not hot. If we look at modeling of temperatures, we can't ever make it where the base is girdled. We can't ever do that. Does that happen? Absolutely. You've seen it. But in our large scale stuff, looking at Eglin, looking at Ordway, we never find it. Never find that to be the dominant driver. It does happen in these stands, but it tends to be really minor. Yeah, Kevin?
Something I took out of my slide, but if you go back to that threshold function of sap flux.
Yep.
One of the things that Joe and Morgan have found in tree stress is that there's that threshold of about 30% consumption of fine roots equals really dramatic declines in the tree's ability to photosynthesize. I don't know if you also produced the graph of your dissertation results that showed a similar curvilinear decline or relationship between consumption and mortality. So mortality rates increase at about 30% consumption at the same time that trees are showing a decline in sap flux or ability to move water at 30% consumption. And so as a manager, and I wasn't going to talk about this, but we can, having a threshold, it allows you to prioritize, right? So 30% seems to be a threshold to kickstart this, what you and Joe talked about as a carbon cascade of insults that the trees spiral into, towards death for a couple of years. That's a neat thing. Maybe we'll pick that back up here in about 30 minutes. We can talk about how we use that to manage mop up and things.
I love that. Yes, sir.
So it's interesting to talk about the fine roots, but I always hear this story at Joy about the taproot and how the taproot buffers longleaf pine from stress. What role does the taproot have in not adequately serving the tree in after these kind of duff fires?
I don't know, that's a good question. I mean, I think, in that surface soil right there, so Joe has always wanted to, and we never did, to look at hydraulic lift in these.
Doing it now.
Awesome. Because that could be that's super interesting, right? If they're pulling water from depths with the taproot, and that water is being dumped into this nutrient-rich, etc., surface soil, and then taken back up with those nutrients, then that's pretty dang cool.
And so I wonder if the taproot, if that's the main point for the taproot, is just to bring it up, let it go into the soil, and then the fine roots have to reabsorb it the next day. I mean, is that
maybe it's I don't know.
outside the realm of possibility?
I don't know. I don't know. It's really cool to think about. I mean, something else that I did not mention that maybe you thought about because you got more sleep than I did was and Joe Hendricks had started some work on this, looking at. I've been talking about all this fine pine roots. What about mycorrhizae? And the surface area that they are generating, the surface area of mycorrhizae that is allowing water and also nutrient uptake is pretty amazing. And taking the fine roots out is a big deal, but perhaps eliminating that substrate for mycorrhizae or the short-term loss of mycorrhizae. What do you think about that?
Something to think about.
Yeah.
Tremendous. Not looking at that.
Okay. What else? We got time for a minute? I love the taproot question though, and the hydraulic lift question. That's awesome.
So talk about and I don't know if Kevin's going to get into this later on, about the importance of these fine roots. And we hear a lot of questions about mechanical disturbances impacting the fine roots. Kevin, are you going to be talking about raking or mechanical operations and their potential impacts on those fine roots, even in the absence of fire?
I was not going to go into a great deal of information or detail on raking, but it does affect your strategy. Maybe Bren wants to get in on that. But
I'll talk a little bit about that.
About raking?
Yeah.
Okay. I can talk about raking as well, so if you want to throw some stuff off.
jump on in and I'll skip.
Okay. Can we talk about raking now?
Yeah.
All right, I'll give a couple things on raking, and then correct correct me later. So I think there are two answers for raking. So when I told James Furman very authoritatively as a graduate student about how to fix this problem, that you just put water on the individual trees, he was very gentle in the pullover. I said, well, you also could do some raking. And he said, you still don't have me. If I'm burning 1,000 acres a day, let's just say I burn 100 acres a day. And he said, you're starting to get at costs that are, let's talk about a threshold. We're either going to burn this many acres or we're going to rake and burn this many acres. It's going to reduce our capacity. He said, some places that's going to work out well. So in the South Alabama site, we could put water on individual trees. We had an ATV tractor and free, graduate student labor walking around putting water on individual trees, and we could save trees. And to some degree, raking is in that way. If it works, it's in that. And I know that there are a variety of experiences folks have had with raking. We installed a raking study at Eglin. It was poorly replicated, poorly designed. It was, I think, a late night, early morning. It was an early morning but late night discussion. And I went out and put in this. I girdled individual trees and I raked individual trees. Girdled trees, if you hack them with a machete, they will die. I did figure that part out. Even Longleaf will die with a machete. And they died pretty quickly. But we did find that there was something like, I don't know what it was, Kevin, 80% or something like that. I'm bordering into anecdote now, but we killed a lot of trees by raking them. When we did some burning at Ordway, we installed a little raking study. We had a light rake and a heavy rake treatment. The heavy raking, I measured productivity, how fast I was moving, doing this. I was in good shape back then. And with the light raking, all we did was remove the surface litter. So basically that apron, we just took the litter off the top. You could see the intact fermentation as an apron. And in those settings, there was no mortality. We didn't get any mortality in that stand anyway. But it was super fast, and you could see flagging on the bowls. So it was a sufficient amount of space away from the stem to reduce the surface heating, and we had no consumption because the underlying fermentation was
That was
wet.
the light raking?
That was the light raking. The heavy raking, we disturbed mineral soil, didn't kill any trees, but again, it was a big study where we tried to kill trees and couldn't do it. Yeah, okay.
Do you think that the raking has a bigger impact on removal of vectors? So how far goes from the surface to the ground is essentially the problem with Duff.
Yeah.
And so removing the pine cones and tree branches, is that more important than removing the litter?
Yeah, and I think that to some degree, it's not that litter is not important. It's just that it flames so quickly. And again, this threshold concept, I could have had a cool figure with thresholds, but I didn't think about doing that. If it's dry enough, surface litter is going to ignite underlying Duff, right? You can have it, and if you've experienced Duff fires, you can have it where you have this pockmarked, oh look over here, there's a little cavity, a little canyon, a little, whatever, like the surface of Mars or something, or the moon. You can see that, and in other sites, the entire Earth is decreased in elevation, much like peat fires or muck fires, right? The entire thing has just been reduced, and those tend to be the drier when it's really dry. The litter is is heating sufficiently to ignite the underlying fermentation that ignites the underlying humus that burns the area completely out. But it's in that sort of tipping point area, Kevin, that you're talking about. It has the cool, which I think is awesome because it does have that cool management levels, right? What you don't want is 256 shades of gray, kind of pick out where you want to be in this, and it's difficult, sorry, it's too complex. What you'd like to have, and what I hope that we get to is, here is the prescription. We have some ideas, Kevin's going to talk about some of this stuff, but sometimes it doesn't work because there is this variability. But thinking about thresholds is nice. You have a go, and you have a no-go. Yes, sir.
So are you getting a sense of how long it takes to get from this bad condition? I've been burning little patches of old longleaf since early 80s. Back to a condition that you would call normal or more manageable, where this is not such a risk. And I'm asking that in terms, I know it's not 2 to 3 years, maybe it's 10, maybe it's 30. In my case, it might be my lifetime.
Right. So Kevin is going to talk about it. Kevin, can I just do one little thing?
Yeah, you can give an answer and I'll take it, right?
Okay. So, Eglin, I can't remember the last time we were there. Kevin, you were still there. We went back to the ranger campsites and looked, and I knew where the trees were, you know, like I knew where the spots were, but it was almost unrecognizable, right? That place looks pretty dang good. So there's some spot, the stuff in South Alabama, we started seeing, the site was harvested. The solar stand was, that's a whole other story. But we started to see a response to the herbaceous. We started to see that mortality, sort of these pulses of mortality were going away. The herbaceous response was super weedy, and so it wasn't like, you know, it turned into wiregrass. And that was, you know, a decade of treatments. And so I came from that, and the sites we burned at Ordway in Sandhills had been 37 years without fire, and they've now undergone 3 fires. And I take folks to the spot at Ordway now and do my little trickery thing, you know, like we have all these trickery sites. We go out and go, oh, this is awesome. So this is really my favorite spot on the whole property. It's beautiful. You know, this is burned, I guess, like 3 times in the last 10 years, 0 times in the previous 37. You know, I don't tell them that. I'm like, isn't this awesome? And they're like, God, this is great. They go for tortoises. Look at all the wiregrass and flowers. This is so incredible. It looks like, and it seems to be functioning like it is a reference condition. And so that is less than 10 years it took to get to that spot. But it's a sand hill that's super low productivity, you know. The site in South Alabama, 10 years, you still walked in there going, ooh, I hate one of these kind of sites, right? You could feel the chiggers drilling into you. And so I think it's super site specific and complex. Kevin?
I think that's right. It depends on the productivity of the site. It seems like these sand hills, the restoration rates, we'll go into that with some data here in a bit. Maybe.
Nice.
Seems like you have a lot more rapid recovery because the degradation is a little bit different than the more productive sites.
Like Orangeburg, Sandy Loan,
Right, yeah.
yeah,
Which is what that site was in South Alabama.
Jackson County, Florida.
Good? Okay.
All right, thank you, Morgan.
Yeah.